And yes, I remember I need to restart recording, resume recording. Okay, recording is resumed now, and so we can continue looking at limits. Now I will switch off probably my camera as always, so that we can simply focus on mathematics. Okay. Please remember to write your name in the chat. Are we there? Yes, we are there. Everything is here. So how many people? 30 people to 28 in chat. So it looks like everybody has written their name in the chat. I seriously do hope that you are not actually practicing the idea that you sign up and then you leave your computer on and then go somewhere else, because that is exactly the situation that promotes all the cheating. And so limits as we dealt with last time. So first of all, we had this idea of a limit. Where we had the starting value, some value of x. You could denote this by x0. Sometimes we denote it by a. It doesn't matter, because what it represents is, of course, some value towards which x tends, or the value that is approached on the x-axis by x. So as x approaches x0 from one side or from the other side, we could see that the function value, in fact, also approaches a certain value, let's say a. The situation with these functions is that the a is not always the value of the function itself. In my case, in this diagram, we had, yes, of course, the function value at x0 is a. It is exactly that value. Sometimes the function is simply not defined at that point. That's a possibility. And therefore, those are the interesting situations. Actually, we are more interested in situations where we cannot find the function value directly. And this is where the limits come in useful to understand the behavior of that function. So we say that a is the limit of a function if the function value can be found arbitrarily close to a, that is, as close as we like, if, of course, the x values are sufficiently close to x0. In other words, as x approaches x0, very, very close as possible and even closer, the function value actually approaches a certain value, a capital. And then we were talking about one-sided limits. We had this situation with one-sided limits. In the same way, if we approach x0 from the right-hand side, then we use this writing. Note the notation, actually, x0 plus 0, like plus something infinitely small, but understanding that it's greater than x0. So x approaches x0 from the right, and on the other side, x approaches 0 from the left. Then we are talking about the left-hand side limit. Then we are talking about the limit from the left, or limit from below, or the left-hand side limit. And as you see, depending on the function, these limits might or might not be the same. And we say that the limit of the function in general exists if and only if both one-sided limits exist and are equal. That is the case in the previous situation. This both limits exist and they are equal. From both sides, the function value actually approaches the exact same value. And of course, the limits are values. The limits are numbers. However, sometimes we will say that the limit of a function is infinity. Sometimes we will say that. However, the finite limit does not exist. Limit is infinity. It is not really a limit. Infinity is infinity. It's not a number. But we do consider the limit of a function when x tends to infinity. So I remember I didn't have a diagram last time. I didn't have a diagram and I had difficulties drawing last time because of some technical problems I was having with my equipment. So the idea was if the function value approaches a certain value as x increases, so the distance you see between the graph and this horizontal line y equals a becomes smaller and smaller and smaller. That is, as x tends to infinity, the function value approaches a. So we can, in fact, consider the limits when x tends to infinity. That simply means that the graph becomes horizontal. This kind of limit is not really infinity, or if this happens to be infinity, that means that the graph behaves somewhat like this, and there's no real limit because there's no number towards which it actually tends. So in principle, mainly we think in terms of limits as numbers. A limit is a number. In some specific situations, it turns out that the limit is infinity, but then we say there's no finite limit. The limit is infinity, which means it doesn't tell us much, really. We are more interested in limits as numbers. With one exception, sometimes a limit is infinity when x tends to a value, to a number. We will see that a little bit later in this slide. So the definitions, again, from last time, a function is infinitely small, called infinitesimal, when the limit of the function approaching that point is actually 0. When the limit tends to 0, the function becomes infinitely small. One example could be, for instance, if we consider the sine function, we understand as x tends to 0, the function value sine of x also tends to 0. That means sine x is infinitely small or infinitesimal if x approaches 0. Or actually the sine function is infinitesimal also as x approaches the value pi. So for instance, we could say that the sine function sine x as x tends to pi is 0, and therefore I would say sine x is infinitesimal when x tends to pi. And we call the function infinitely large when the function value tends to infinity when x approaches x0. This is mostly the situation where the function, normally as we understand it, is not defined. For instance, okay, sorry about the skewed curve. For instance, if we talk about the function y equals, let's say, 1 over x, you know from school that the graph is a kind of hyperbola, like this, the inverse variation function, and we see when x tends to 0, the function value becomes infinitely large. The function value becomes infinitely large. It simply means that as x becomes very, very small, infinitesimal x, the function value actually becomes very, very large. That is infinity. So in this case, it is probably the idea when we might allow division by 0. Normally, we say we cannot divide by 0 in algebra. In the whole mathematics, we say division by 0 is not possible. But when we deal with limits, x is not really 0. X tends to 0. It becomes infinitesimal. It becomes very, very small, infinitely small. We are not talking about x is 0, because when x is 0, nothing happens. The function doesn't exist. But when x approaches 0, then the function becomes very, very large. So let's understand that when we are talking limits, 0 is not really a number. Real 0 is a limit. 0 is something towards which the function or the x value tends, approaches 0, but not necessarily is 0, because we are looking everywhere except that point. When we deal with limits, x tends to some value x0, it doesn't mean x is, x approaches this value. So the whole idea about limits is approaching infinitely close, approaching some value very, very close, not necessarily reaching that value, just approaching. That's the whole idea of limit. So you see, in calculus, starting with limits, the thinking required in mathematics is completely different from the usual thinking in algebra, vector geometry, analytic geometry, linear algebra, everywhere else, because the calculus part of mathematics is about a process, about what happens as we approach something. So if x approaches something, it's like a process. We are thinking of x doing something, not x being equal to, but x doing something. So calculus is about process, about things happening. So limits is actually a new level of thinking, because it requires thinking that it's happening, we are approaching something. Even we might say it not necessarily happens in time. With respect to time, we can actually think of it just on the geometrically. Still, however, we deal with this as with a process, with something going on. And so infinitely large is if the function values become very, very large when x values approach a certain value. In this case, x approaches 0. I could say limit when x approaches, and now basically I have two one-sided limits. By the way, x approaches 0 plus 0. So from the right-hand side of 1 over x, we see that the limit is plus infinity, the function tends to positive infinity, and the left-hand limit, x tends to 0 but minus 0 from the left of 1 over x, is negative infinity, because as x approaches 0 from the left, you see what happens with the function. The function goes down. It becomes infinitely large, but negative. So the matter of definitions. And this was this next definition where the function is bounded. So if function is bounded above, bounded below, we had this idea as well. So if on a certain segment, we are not talking about the whole domain, all possible values of x, it's enough that we are considering some segment from A to B, and if in that segment the function value is all below a certain value m, then we say the function is bounded above, because the function does not rise above this value of m capital. And also, I noted last time, if one m value like this exists, it could be another one, because this also follows the same rule. Or maybe we could set the upper boundary a little bit lower. Of course, there might be sometimes the lowest possible value, the least possible value of this m, but not necessarily. For us, the point of interest, the moment of interest is that it simply exists. Yes, of course, if one such value, m, exists, then infinitely many other such values exist, all of them above, for example. And similarly, a smaller value, m lowercase, where the function, we can see the function is all above this level. All function values are greater than the m lowercase value. So bounded altogether is simply, it means that the function value is squeezed, like in the squeeze theorem, between two values. And this is important because this plays a certain role with limits. Now, properties of infinitesimals and infinitely large functions. This is what we skipped last time. This is what was not considered last time because we went on to some examples directly. We also discussed the limit laws, some theorems like the squeeze theorem, the uniqueness of a limit, the comparison of limits. So if two functions can be compared, one is greater than the other, then the limits have the same relation. But we skipped this part because we moved directly to some examples. So properties of these infinitesimals, infinitely small, and also of infinitely large functions. In a way, they are both infinities. The small infinity, the zero infinity, that is infinitely close to zero, and the large infinity, that is simply infinitely large as we like. So the reciprocal, remember the reciprocal of a number A is the number 1 divided by A. If we talk fractions, we turn the fraction upside down. So what happens if A is an infinitesimal? Its reciprocal turns to be an infinitely large function. But of course, we don't generally, it would not be correct to write this. Normally, it's not correct to write. If you have to write this, then please put it into quotes, because this would mean that we are not really talking about division by zero. We are talking about division of an infinitely small quantity, about division by something that approaches zero, really, really close, but not by zero itself. And therefore, we should put these quotes, because this really is not an algebraic operation. It is the idea of limit. You see, if the limit of function f is zero, then the limit of 1 over f is infinity. We do not normally, officially in mathematics, we do not normally write this 1 divided by 0. We would like to, because we don't like to write too much. We, of course, all of us prefer to keep our writing short. Nobody likes to write much these days. But if you really have to do this, then please put it in quotes so that understand that you know it's not really division by 0. Not really. Is division by something that is very, very close to 0, and the result is something simply very, very large. And the other way around, the reciprocal of an infinitely large is an infinitesimal. Again, the same situation. It's like, yeah, dividing by infinity. We cannot divide by infinity. Infinity is not a number even. But we think if the denominator becomes very, very large as we like, we can make the fraction value very, very small. That is, we can make it approach 0. Again, using the quotes, because this is not an official mathematical notation, this part. This is, the limit part is official, but this part is not. However, during the process of work, it is often necessary to note, to demonstrate that we see the situation, we evaluate the situation, like make a very short note about the situation. So that's when we write this 1 divided by 0, 1 divided by infinity, but in quotes, because we want it to be mathematically correct. And of course, instead of 1, we might have any number. We will see a little later. We will see it a little later. So even if I have, instead of 1, I have some very small number like 0.00001, it's still a constant, and a constant divided by something very, very small in the end will be something very, very large. So instead of 1, one moment, I have to connect my computer to the electricity. Okay, to the charger. Okay, there it goes. Right, so we move on. So the product of an infinitesimal and the bounded function is an infinitesimal. That is, the bounded function is limited. The bounded function is bounded between two values. So in principle, if we have an infinitesimal, and by the way, infinitesimals are often denoted by Greek letters, like if the function f of x is infinitesimal, when x approaches x0, we quite often denote it using Greek letters like this. So if I write alpha of x or beta of x, I usually write down that this is an infinitely small function as x tends to something, but basically it's also demonstrated by this kind of notation. So basically, suppose that we have alpha, that is this infinitesimal, multiplied by a bounded function f. This means if f is bounded above, it means that its value is less than m capital. So I have it's less than, this product is less than m times alpha of x. And at the same time, greater than m small times alpha of x. Because remember, I am considering f a bounded function. So if f is a bounded function, if f is a bounded function, and we do this, then basically we see constant times infinitely small. It doesn't matter how many zeros you add up, you still get 0. So a constant times something infinitely small, the limit of this is also an infinitesimal. Constant times an infinitesimal is infinitesimal. Constant times infinitesimal on the other side is infinitesimal. And by the squeeze theorem or the sandwich theorem, according to those, you see that if the limit of these two functions both is 0, then our function bounded times infinitesimal, also the limit of that is 0. So this is, let's say, a very quick proof, or at least some understanding of why this happens. So if I have an infinitesimal times constant, the result is still infinitesimal. So that's something that is not stated here, that seems to be, let's say, well understandable. So if I have a constant times infinitesimal, I get an infinitesimal. If I have constant times infinity, even if the constant is very, very small, then the result is, of course, infinity, infinitely large function. Again, we are talking about limits here. We are not multiplying by infinity as such. We are understanding we multiply a certain constant, 10, 5, minus 3, by something infinitely large. And of course, the result will be infinitely large. The sign, plus or minus, will evidently depend on the sign of the constant and on the sign of this infinity, right? And the constant times 0, that is constant times infinitesimal. Constant could be very large, like 1,000,000, but 1,000,000 times something that tends to 0 will still tend to 0 in the end. That's the interesting property of limits. This is the interesting property of limits. It might not be 0 itself, but if we multiply it by a constant, the result will also be, not maybe 0 itself, maybe not 0 itself, but it will approach 0. The limit of this will be 0. So the thinking about limits is somewhat different from thinking about numbers. The simple reason being that our mind is finite. Our mind is not equipped to deal with infinity. We can perceive numbers. We can imagine very clearly what a number is, but it's very difficult to imagine infinity for our mind. And therefore, the limit operations sometimes might feel somewhat confusing. So that simply means that we need to practice. More properties. the ratio. Remember, we had the law of limits about dividing the limit of the quotient of two functions. We said the limit of the function f of x divided by limit of the function g of x is the quotient of the limits. We could take these limits separately, right, and divide those. However, if they are both infinitely large, we get something like infinity divided by infinity. What's that? Is that 1? Is that 2? How do we know how many times one infinity is greater than the other infinity? We can't really know. So the ratio, this ratio could be any number. For example, if I have, for instance, if I have the function x squared when x tends to infinity, for instance, and the function 5x squared when x tends to infinity, the ratio of these two functions is 5, although it is infinity divided by infinity. At the same time, I could have x squared tending to infinity and x cubed tending to infinity. And when I try to divide these functions, the result is not really a constant. So it turns out that one of them is infinitely many times greater than the other function. So this can be anything. The ratio of these two, of any two infinities, it can be 0, it can be any other real number, it can be infinity. That's a problem which calls for a specific solution. We cannot really immediately see what is going on there. Usually this happens when x tends to infinity, but sometimes it might be possible this thing happening when x tends to a certain value. And similarly, if they are both infinitely small, what happens when we have to consider alpha of x divided by beta of x, where they are both infinitely small functions when x tends to whatever it tends. So again, it's not really 0 divided by 0. This is the quotient of two things, of two functions that approach, both of them approach 0. So we want to see what the ratio, what the quotient of these functions is when they are both so very infinitely small, what the quotient is. And again, yes, surprisingly, that quotient can be 0, can be any other number, can be even infinity. So two infinitesimals, tiny, tiny quantities, but one of them is still infinitely many times greater than the other. Mind-boggling. And such cases are called indeterminate forms. We may say uncertainty if we want to say it very quickly, but it's called indeterminate forms, because the result, these indeterminate forms, so in this case, we may write without the quotes, because this is quite often used in official papers, officially. So indeterminate, because if we look at that limit without analysis, if we look at this situation, it's not determined. There's no one specific number. In each case, it will be something different. That's why we say indeterminate forms. And this is the situation where we cannot simply plug in the numbers. Remember last time in examples, we simply plugged in the numbers. In these examples, for instance, we put in x is 0 in this, and we saw, oh, this limit is -6. Because when x approaches 0, it's very clear that the value of this function approaches -6. So this limit was -6. And we said, okay, x tends to 4. That means x squared, 16 minus 4 divided by 1 minus 4, 12 divided by -3 is -4. So that limit can also be found by direct substitution. By direct substitution, this is called direct substitution. Even here, when we think, okay, it's constant divided by infinity, now we can say that this limit actually is the limit 5 times 1 divided by infinity. Looks absolutely crazy. It's 5 times 0, so it's 0. This limit is 0. Because remember, 1 divided by infinity, the reciprocal of infinity, the reciprocal of an infinitely large function is an infinitely small function. And similarly for this, we could say that this is 10 times 1 divided by x tends to 5, so that would be 0 squared. 0 squared, I write the square to stress that this will be positive 0. So 1 divided by 0 squared is actually positive infinity. To stress the fact that the result is a positive infinity, I would still write the quotes there because you cannot multiply by infinity any more than you can divide by 0. So we think, okay, constant divided by infinity is 0. Constant divided by 0 is infinity, but that's more or less colloquial, everyday thinking. It's not, let's say, mathematically correct. If we want to write a mathematically correct paper, a thesis, for example, then we would need to use the exact, precise, correct notation. Now the remaining exercises, the EFG that we did not consider last time. So this, let's have a look. Looks like direct substitution will work. We write limit.
Excuse me, miss.
Yes.
Can you show previous slide for a second? Okay, madam. Thank you.
All right. So again, this is what we call the direct substitution. So by direct substitution, we can see, basically, we don't have to write limit anymore. I'm sorry, we don't have to write limit. If as soon as we substitute numbers, as soon as we don't have x anymore, then we don't have to write the limit. So 5 minus 3 to 0 power 3 plus 3 to 0 power is 5 minus, remember, any number to 0 power is 1. 3 plus 1, so we have 4 over 4. This limit equals 1 in E. In F, again, we can try direct substitution. Let's see, minus 5 minus 1 is minus 6. 3 minus 2 times minus 5, negative 10. 3 minus negative 10 is positive 13, and 4 times minus 5 squared is 25. So we have minus 78 over 100, so minus 0.78. Direct substitution. But these situations are rare. These situations happen very, very seldom because, in general, they are not interesting for mathematics. Limits are interesting and necessary specifically for those cases where we cannot find the function value directly. In these cases, basically, yes, we can evaluate everything. So, in principle, the uncertainties, these indeterminate forms I discussed in the previous slide, are the situations where limits are the most needed. Here we can see 2 times 0 cubed by direct substitution plus cosine of 0 divided by 0 plus 3, 0 plus 1. And we see 0 plus cosine of 0 is 1. And here we have 0 plus again 1. So 1 divided by 1 is 1. Again, so we can find all these limits. In principle, we substitute the x value. Well, it's not very nice to substitute infinity, but at least we understand what is going on with these infinitesimals and infinitely large quantities. We at least understand what was going on. And if we can plug the numbers in, then even better. So our problems, of course, start when we have infinitely small and infinitely large functions, But first of all, let's go back to one-sided limits. Let's consider some one-sided limits, because in some situations it's also important to understand, are we having a positive infinity or negative infinity? For example, for this. Let's think. If we are considering the limit from the right, that is x tends to plus 5 plus 0, the first of the limits, that is x tends to 5 from the right, from above. That is x minus 5 tends to 0, but to a, so to say, positive 0, because x approaches 5, x is not exactly equal to 5. It's, let's say, by an infinitesimal, by a tiny quantity, greater than 5. So this difference will be plus 0. But in principle, we can still take this and plug it into the one-sided limit. It helps. So if we substitute directly, instead of x, we write 5 plus 0 minus 5. You see why we need this notation, 5 plus 0, for one-sided limit, because now 5 minus 5, now these are constants. This 0 thing, this is not a constant, but 5 and 5 are constants, they disappear, so we have 2 divided by positive 0, and that will be positive infinity. On the other hand, if we have this other limit, when x tends to 5 from the left, so minus 0, this other one-sided limit, we can again write 2 divided by 5 minus 0 minus 5. 5 is always considered a constant, only 0 is considered an infinitesimal. So we see now 2 divided by minus 0, because constants can be cancelled. And that means positive constant divided by infinitesimal, which is negative, gives us a negative infinity, the minus infinity. So this is the thing that I want to consider. That was A, situation A. Now let's consider the situation B. This is somewhat more complicated. Because x tends to minus 2. So yes, x squared does approach 4, but we have to be very, very careful. Because when x approaches minus 2, let's consider the graph, because I will need to erase this. Please make sure you are copying and writing things down, because I will need to erase this to make more space for C. We may not consider, for example, D. That perhaps is not so important, because it will be somewhat similar to B, but C needs to be considered, and we will need more space for that. So if we are talking about x squared, now imagine the function x squared. It's not this function, but I'm simply talking about x squared as such. So what happens when x approaches minus 2? If x approaches minus 2 from the left, so that will be minus 2 minus 0, this limit. Minus 2 plus 0, so x tends to this. Look what is happening here. Yes, x squared does tend to 4, but if x comes in from the left, then x squared tends to 4, see, from above. So x squared approaches 4, but is greater than 4. And if x approaches minus 2 from the right, from above, we see that x squared in this part is less than 4. So basically, we see that this difference will have the opposite sign to what we think it might be. 5 divided by x squared minus 4. You see, if x approaches minus 2 from above, from the positive side, the x squared is So this means x is greater than minus 2, but x squared is less than 4 in this situation. In this situation, we have to think very carefully, because on the right-hand side, the absolute value of x is less than 2. So this will mean 5 divided by minus 0, which means negative infinity. However, yes, you can also put in this minus 2 plus 0 instead of x and then make the square. That's going to be even more interesting, but then that requires understanding of infinitesimals of higher order, so we are not doing that. And in this case, in the second case, we see that x is from the x comes in from the left. If x comes in from the left, it's less than minus 2. However, x squared is greater than 4 in this second situation. That's this case. And that means it's 5 divided by plus 0, because x squared will be greater than 4. And so in this case, it's plus infinity. So it's not always x approaches the value from the left, so it will be negative. Then the limit will be negative. From the right, the limit will be positive. You see how we have to think very, very, very carefully about this. Okay, I think I can afford now to erase this parabola. It was only needed to explain how things are visually. However, you should all understand this framed thing. So I am erasing the parabola at the moment. Not everything, but just this. Because it was a demonstration, and the parabola is not the graph of the whole function we consider. The parabola was only to illustrate the quadratic thing. All right, somebody is 43 minutes late. And finally, the C case. This function. This is something quite interesting now. Let's see. We have to discuss the limit when x tends to 2 from the right of 3 to the power x, 1 over x minus 2. Of course, x cannot be equal to 2, we understand, because then we have to divide 1 by 0. That would mean 3 to power infinity or something. That's not something very nice. However, if we discuss this, so let's see, if x tends to 2 plus 0, then we could understand that x minus 2 tends to positive 0. We can sometimes write using approaching the arrow to demonstrate that things approach. If we want to skip the writing a little bit, if we want to skip this somewhat, then we can write using arrows instead of limits. So x minus 2 approaches plus 0, which means 1 divided by x. What?
Ma'am, can you explain that B once more, ma'am?
Who's asking? Someone who came late?
No, ma'am. I'm okay.
Okay. In B, we have to understand that x squared, if x squared tends to 4, which happens if x approaches minus 2, x squared approaches 4. The big question, so when x tends to minus 2, x squared, of course, tends to 4. The big question is, when it tends to 4, does it stay greater than 4 or less than 4? Because on that, the sign of the 0 here will depend. The sign of the 0 depends on whether x squared in this approach, in this process. That's why I stressed today that limits is all about the process. X goes to minus 2, but it's greater than minus 2. This means it goes to minus 2 from the right. from the right. So think about the parabola. The function value goes to 4, the square goes to 4. Yes, indeed, the square approaches 4, but you see from below, because it's the left-hand half plane of coordinates. It's the parabola to the left of the y-axis. So x stays greater than minus 2. However, x squared, you see, stays less than 4. That's why this is actually less than 4, and that's why the 4 minus 4 difference is negative 0, because we have 4, but a little bit less than 4, minus 4 exactly. So we have a little bit less than 0, and therefore we have the negative infinity. And similarly, from the other side, if we approach minus 2 from the left, the x is less than minus 2, but x absolute value is greater than 2, and so the x squared is greater than 4. And therefore, this difference tends to 0, but stays positive. This is the way of reasoning we have here. This is the way of reasoning we have here when understanding the signs of infinity.
Okay, ma'am. Thank you.
Now I'm moving back to that situation. So we are looking at the two cases where x tends to 2. So if x tends to 2 from the right, staying greater than 2, then x minus 2, of course, tends to 0, but stays positive, because x stays greater than 2. We remember that for the one-sided limit, for the limit from the right, from above, x tends to that value, but staying greater than it, in this case greater than 2, which means x minus 2 tends to 0, but positive 0, which means this is, well, tends. This tends to 1 divided by positive 0. Thus, this means positive infinity, right? So in this case, so this is basically the analysis of the situation, explanation of why we know the answer is what it is. This is 3 to power positive infinity. Again, I am putting it into the quotes because we cannot take 3 to infinity. We can only take 3 to a certain power. But if this power becomes very, very large, this is where it is important that you remember the basic elementary functions. And this is one of the reasons why we started 2 lectures talking about functions, not limits yet. Because remember now, again, it's in this appendix to the first lecture of this unit, the functions. If the base of exponential function is greater than 1, this function is increasing. The graph looks like this. So when x, the exponent, tends to infinity, increases, the function value 3 to power infinity also tends to infinity. So the limit, when x tends to 2 from the right of this very interesting, complicated function, is plus infinity. Now let's consider the other one from the left. When x tends to 2 minus 0, so from the left, 3 to power 1 x minus 2. Let's see. If x tends to 2 from the negative side, this means x is less than 2. That means x minus 2 tends to negative 0. It does tend to 0 because x does tend to 2, but because x is staying all the time on the left side of 2, approaching 2, but staying less than 2, then of course this limit, this value tends to 0, but staying on the left of the 0. So we can write negative 0, that is infinitesimal but negative. Infinitesimal but negative, which means 1 divided by x minus 2 is 1 divided by, so to say, negative 0, and that will be negative infinity. So this means that, okay, I'll draw the line here. This limit now is actually 3 to power negative infinity in this case. But we see if x tends to negative infinity, then exponential function, so 3 to power x, or in this case, the exponent is more complicated, but if the exponent tends to negative infinity, then the power of 3 actually tends to 0. This is something very interesting, very interesting, because let's see what the graph of this function might look like. Might. I'm not saying it looks exactly like that, but the general idea. What can we conclude about this graph? So our problem is when x is 2. Okay? So if x approaches 2 from the right, the function tends to plus infinity. All right, so I can draw a vertical asymptote and say the function goes to positive infinity. The graph goes up. I don't know what happens here further on. I don't exactly know what the behavior of this function is. However, 3 to any power, you know that 3 to any power is always positive, so I'm not going there below the x-axis with the graph. However, when x tends to 2 from the minus side, we see the function value approaches 0. But of course, we cannot find the function value at this point. So this point is empty, but the function value approaches 0. It goes towards 0. However, the point itself is empty. The point itself is empty, simply because the function value cannot be evaluated. The function, this thing, cannot be evaluated when x is 0, because you cannot divide by 0 as it is. This is where the limits come in very useful. We understand that the function value from the left actually, yes, at this point does approach 0. By the way, it's always positive. But again, we don't really know how the function behaves. But we know that around 2, the given function shoots off to the positive infinity on the right-hand side and goes here to 0 on the left-hand side. So that would be a very interesting graph, but we are not investigating it any further. It's not an accurate graph. I'm not finding any exact values. I'm simply seeing what must happen. And of course, I understand that the function will be always positive. So this function is, as you see, for this function, limits are essential, because otherwise, how do we know what the graph might look like? So this is a very interesting moment. I am skipping D at the moment now. If necessary, we can return to this next week, perhaps. So, but the answers are all in the lecture file, by the way. So you can try and see and understand why the answers are as they are. And we are now moving on to the next. So properties of infinitely small, infinitely large. Some limits. The colors are unimportant, blue and orange, because I didn't want to keep the whole slide in the same color. That's just random colors. Now let's see, the A situation. So when x tends to negative infinity, when x tends to negative infinity, we don't know what happens to the sign value, because sign, basically, it will fluctuate. But sign function is bounded. So when x tends to negative infinity, we understand that the limit of 3 to power x only, when x tends to negative infinity, is, of course, 3 to power negative infinity. We just saw it's 0, because the exponential function of a base greater than 1, we know how it behaves. So knowing the basic graphs is essential. So you should investigate the table of functions. memorizing a little bit about the graphs. So this function 3 to power x is infinitesimal. When x tends to negative infinity, what happens to sine x? Sine x, as I said, it fluctuates between -1 and 1, but that simply means that sine x is a bounded function. It's less than or equal to 1, greater than or equal to -1. That's by definition of the sine function. And so we see infinitesimal times the bounded function. Infinitesimal times bounded is infinitesimal. And therefore the given limit is equal to 0, because infinitesimal times bounded is infinitesimal. So in this case, what was important was understanding that sine function is bounded and that 3 to power x is infinitesimal. Understanding the components. As soon as we understand the factors, the components of this limit, things become all right. Next, B. We see infinitely large, x is infinitely large. So this actually becomes like infinitely large. LG of x, logarithm, decimal logarithm of x, logarithm to base 10. We will discuss that in the elementary mathematics, but let's just remember that LG of x means the same as logarithm to base 10 of x. We don't use notation logarithm without base, because that leads to contradictions. So we write either log to base 10 or LG, not simply log. Anyway, we know that when x tends to infinity, because there's no minus, we mean positive infinity, the logarithm is to base 10 greater than 1. That means the logarithmic function is increasing, which means when x tends to infinity, the logarithmic function also tends to infinity. So this is basically positive infinity times positive infinity. So this limit is infinity. I should write in black, I guess. So is infinity. Positive infinity, by the way, but if we do not write plus in front of the infinity, we still understand it as the positive infinity, just like with positive numbers. If we don't write the plus in front, we still know it's positive. C. Now what happens? Can I write with black there? No, not very visible. Negative infinity. Well, let's understand 3 to power negative infinity. Let's remember again, when the base is greater than 1, then the negative exponent means this situation. That means I actually have, 3 to power negative infinity plus the same with 4 to power negative infinity, which is not really correct, but we can write if we put it into quotes, understanding this is not about numbers, this is about limits, and that means it's 0 plus 0, so these two limits separately are zeros. Of course, the sum of two zeros is a 0. Two infinitesimals added is an infinitesimal. And D is interesting. Now I'm switching back to white pen. In D, what happens in D is we have two different powers of 2. They are divided. I would advise you to simplify this expression. So 2 to power minus 2 is in fact 1 divided by 2, properties of powers. So we have 1 divided by 2 to power x and again divided by 2 to power x, simply moving the negative exponent downwards, right? So we have limit x tends to infinity, 1 divided by 2 to power x times 2 to power x. You have two possibilities, two options. You can write 2 to power 2x, adding the exponents, or you can write 4 to power x, multiply the base. So, all right, let's write 2 to power 2x. And x tends to negative infinity. I wrote positive, forgot the minus. I meant, of course, to write the negative infinity because the limit has negative infinity. So this means 1 divided by 2 to power negative infinity. 2 to power negative infinity is 0. So this means, okay, limits. It's all about limits. 1 divided by 0. And 1 divided by 0 is, of course, the limit is infinity. Let's remember one thing. 2 to power whatever is always positive. And therefore, 1 divided by the positive 0 is, of course, the positive infinity. So I'm stressing the fact that this is the positive infinity. You don't have to write plus infinity, but it's good to be aware, to remember that sometimes we might get a negative infinity. That's when we need to stress it. Now, E. All right. Arctangent x, x. X tends to positive, negative infinity. One thing we should remember, again, when x tends to infinity, positive, negative, what happens to arctangent? Again, this is where we have to remember properties of functions. And you should also remember, we actually dedicated some time in class for these inverse trig functions. And the arctangent function graph, it is in the second lecture of this unit. If you need to look up the lectures, which I strongly advise, because I do have a feeling that there are many people who don't even take a look at the lectures, who don't even take a look at the formulas that I always put on the right hand of the slide during tests. So do that. And we have the arctangent graph. We had it in the lecture and we had it in the lecture file. It is in the lecture file. The arctangent. Sorry, what? Minus pi by, okay, the function, but what matters here is that it is bounded. In this case, it is bounded. So in principle, here we have arctangent is bounded. So the explanation would be, yes, between pi half, pi over 2, and minus pi half. Arctangent of x is bounded. So what we actually have here is the limit when x tends to positive, negative infinity. At the moment, I am not separating it. We have arctangent x times 1 over x. 1 over x is evidently, so I'm putting this in brackets because it's all the same limit. What this means, it's positive or negative 0. This would be positive or negative 0. So basically we have a bounded function. Again, the bounded function, or I will write bounded times positive or negative 0, because we have 1 divided by infinity. So times positive or negative 0. This is, as I repeat, this is not official mathematical notation, but you may write it like this. If it's clear what you mean, I will accept writing like this. So bounded times infinitely small is infinitely small. It's 0. The limit of this is 0 at both ends. At both ends. And actually, it's always positive 0, because if x tends to plus infinity, arctangent tends to pi half, but is positive and divided by positive infinity. Positive divided by positive is positive 0. And if x tends to negative infinity, arctangent value tends to negative minus pi half. And divided by negative infinity, the result is still positive 0. So the result in both cases will be positive 0. So the arctangent function will actually approach positive 0. This function, arctangent divided by x, actually will always be positive. Of course, we will have a problem. We will have a problem when x approaches 0, because then we have arctangent of 0, 0 divided by 0. So when x tends to 0, the situation is different. We will consider it, I do believe, next week, next lecture. So that will be again different. So while x only tends to infinity, so at both ends of the graph, we understand that the function value tends to 0. The function value is infinitesimal. F. Now, all right, this was E, took up quite a lot of space. F. When x tends to minus 2. Let's try to plug numbers in. Minus 2 plus 5 divided by minus 2 squared is 4 plus 3x, that's minus 6 plus 2. So we have 3 divided by 0. 3 divided by 0 is, of course, infinity. In this case, again, in principle, we should consider tending to minus 2 from the positive or from the negative side, from the right or from the left, because the situation is such that at minus 2, the function is not defined as it is by itself, and it could be positive infinity or negative infinity. This is slightly, let's say, slightly slippery, because we are not considering here, as we should, the one-sided limits. The one-sided limits would be with different signs. But in this case, infinity is enough. Similarly, in G, x tends to pi half, and to be honest, tangent x could tend to positive infinity or negative infinity. When x approaches right angle, the tangent value could be positive or negative infinity, but as such, we have 2x, so 2 times pi half, divided by positive or negative infinity in this case. Constant divided by infinity is, of course, 0. Constant divided by infinity is 0. And in the last case, if we consider positive infinity, we could think x, that would be infinity, x tends to infinity, ln of x. Now, ln of x is the natural logarithm of x. This means logarithm to the base magical number e. E is approximately 2.72. So this is again a function that is increasing. So when x tends to infinity, the logarithm, natural logarithm of x also tends to infinity. And now we have minus 2 to power, evidently, if this is positive infinity, 2 to power negative infinity. Remember again, if x tends to negative infinity, 2 to power x, the function that is increasing, tends to 0. However, of course, infinity minus 0 is infinity. So this is how we can evaluate limits using infinitely large, infinitely small functions. For instance, you can use, if necessary, in A, we can use the squeeze theorem directly, or we can simply write infinitesimal times bounded and write down the answer. So the main thing that is important is that you can consider the function, consider the expression, and understand what is going on there. because in many cases, as you see, there are functions whose values cannot be found. They simply cannot be found directly, so you have to consider limits. And now, how to find limits specifically? We have some 20 minutes remaining for that. And next time we will continue with these exercises from finding limits. Evidently, there's not enough time to do absolutely everything. However, we'll do what we can. So first of all, you already see that in this topic, we will look at indeterminate forms, 0 over 0, how to resolve it, how to find that limit in each specific case separately. Because in general, 0 over 0 could be anything. So in each case, we will do maybe something slightly different. Infinity divided by infinity, the same thing. And then infinity minus infinity, it could also be anything, because two functions could be so close that even in infinity, their values differ very little by a constant, for instance. The functions could be so close that even they both tend to infinity. We see that one function is, for example, 3 times greater than the other function. So the difference of these would still be 2 infinities. So this is also an indeterminate form, because the difference of 2 infinities could also be basically anything. Could be infinity, could be constant, could be 0. And so, how do we do these things? So this, if we put in the numbers, we clearly see it is 0 divided by 0. So this is an indeterminate form. We don't exactly know what to do, how to deal with this. Now, what should we do with it? So the answer to this situation is, basically, when we have rational functions, that is polynomial divided by polynomial, we try to factorize them. If we have 0 over 0 and the rational function, let us factorize. So we go on, it's still limit, we write limit all the time while we have x. We only stop writing the limit sign when we have pure numbers without x. So as long as we have an x in the expression, we have to write this limit thing. I know people hate writing this and many times skip the writing of limit. That's incorrect. So taking x, factorizing, taking x outside the parentheses, 3x minus 2, and in the denominator we have x, and here we have 2x minus 5. Now you see, the top part, the numerator, tends to 0 because it's something multiplied by 0, by x. The denominator tends to 0 because it's, again, some expression multiplied by x, by 0. So it's a good thing then that we can simply take and simplify, cancel out the x. And now, when x tends to 0, we see 3 times 0 minus 2, 2 times 0 minus 5, that's 0 minus 2, 0 minus 5, or negative 2 over negative 5. So that is positive 2/5, or 0.4. So it turns out that this limit actually has a rational, normal, perfectly normal number, a value. But we could find this value only because we were able to cancel out those factors that make the 0. So when we have, the first rule would be, if we have the indeterminate form 0 over 0, the first rule is try to factorize. Try to factorize. That will be the first possible approach. Factorize and cancel out. Factorize and simplify. And when you have simplified the fraction, then you will many times, in many cases, most cases, you will be able to evaluate that limit. This is in some cases we might need to factorize things somewhat differently. So I am going to write another example, limit when x, for example, tends to 3 of x squared minus 9 divided by x squared minus 2x plus, no, not plus 1, plus 3. And it's 3 plus 1, yeah. So this is again, you see, it is 9 minus 9 over 9 minus 6, minus 3. Minus 3, I put minus 3 in there. So I invented this example. So we see that this is 0 over 0 again. Which means, again, I need to factorize. So I'm writing the limit when x tends to 3, factorizing x minus 3, x plus 3. And again, this is one of the reasons why we discuss factorizing and simplifying rational expressions in elementary mathematics. So we would say x minus 3, x plus 1. By factorizing this, now we see x minus 3 can be cancelled out. Fortunately for us, this is the factor that creates those zeros. And it can be proved and demonstrated by theory of polynomials that this is what is going to happen. If you can factorize these expressions, then one of the factors will be the zero factor, the evil thing that creates zero. And it generally is going to be the same in the numerator and in the denominator. So if you can factorize the polynomials, then one of the factors is likely to be x minus that evil number. And so now we can use direct substitution. If x tends to 3, we have 3 plus 3 divided by 3 plus 1, so that's 6 over 4, or 1.5, or 3 halves. And that's it. We will see. If you have polynomials and it is 0 over 0, then it is possible. The problem might be you don't know the method how to do this, but I'm not going to give you fifth or fourth order polynomial to factorize. If it is not possible, if in principle a polynomial cannot be factorized, then that means it shouldn't be 0. It shouldn't create the 0. Because the theory of polynomials tells us that if a polynomial is equal to 0, then it can be factorized, and one of the factors is x minus that value. One of the factors is the factor that creates the 0. That is from the theory of polynomials. So other functions, if we don't have a polynomial but something else, then yes, we will have a special approach. For now, the same function, now please pay attention, it's the same function, but now x tends to infinity. So this is now, we have a complete confusion at the moment, because we have infinity minus infinity, infinity minus infinity. Basically, we have infinity over infinity. We have no idea what is going on there. So what we do is not factorize, but something similar to the previous case, because in the previous slide, what we did was we divided out the 0 factor. We canceled out, we divided out the evil factor. The evil factor in this case being the factor that creates the zeros. So in the next case, we will also divide out the evil factor that creates, in this case, infinity. So what we will do, limit when x tends to infinity. We can factor out, we can take, for example, simply divide out the greatest power of x, the greatest power of infinity is divided out, but the greatest power of them all. So we can factorize, but the factorizing is a little bit different from the previous case, because we take the highest power of x. The highest power of infinity should be taken out. So if I take out the highest power x squared, the highest power x squared, then that leaves me with 3 minus, what happens if I take x squared out of this? 1x is taken easily. So if I divide this by x squared, I actually get 2 divided by x. Just think mentally, check if I multiply these, I will get 2x. Fine, it's correct then. In the second case, if x squares out, then we have 2 and minus again 5 over x. If 5 over x is multiplied back by x squared, we would get 5x. So things are correct. Now we can cancel out the bad, evil factor, that is x squared, which creates the infinity. Now we have 3 minus 2 divided by infinity, remember, is 0. 2 minus 5 divided by infinity, remember, that's 0. So this limit is 3/2. Another approach, another way in which we might write this limit x tends to infinity is we simply divide numerator and denominator by the highest power of infinity that we see there, the same. You know that properties of fractions allow us to divide or multiply the denominator and numerator by the same value, the same number, except for 0, of course. The property of fractions AC divided by BC is the same as A over B. So we can actually divide out the, whatever factor with numbers, common factor, but as it is, whatever factor. So now what happens, we rewrite this. This is simply another way of doing the same thing. You may choose. You may write it like this if you understand this easily. If not, just remember we divide out the highest power. So we have 3x squared divided by x squared minus 2x divided by x squared. This will give you, let's say, an more easily understandable answer, perhaps. 2x squared divided by x squared minus 5x divided by x squared. So divide both numerator and denominator by x squared because that is the strongest infinity. If x tends to infinity, then x squared tends to infinity times infinity, infinity squared. So it's a stronger infinity. Now to simplify, and we get the same thing as before. We see 3, we see it's 2 over x. After simplifying, we see it's 2, we see it's 5 over x. So it's still the same. 3 minus 0, 2 minus 0, same thing. So you may take the highest power of infinity of x out of parentheses and simplify this way, or you can think, okay, let's just apply to every term. Let's simply apply this division by x squared. Because why x squared? Because we take the highest power. The highest power of infinity. And in this case, x is the infinity. X tends to the infinity. The highest power of, sometimes we take not the highest power of, yes, what? Okay.
Ma'am, if the question was like limit x tends to negative infinity, this function, then how it will be like?
We will still take out the highest infinity. We'll still would take out x squared. The same thing. So if x tends to negative infinity, the difference is that this this will tend to positive 0, which makes no difference. The limit will be the same thing.
Okay, ma'am.
The limit will be the same thing. So in most cases, it's absolutely unimportant whether we have positive or negative infinity. Most functions might have the same limit. Okay, next. Let's have a look at what is next. Another limit. So another limit, x tends to 1. So let's try 1 minus 1, 1 plus 2 minus 3. It's again 0 over 0. You can put it in quotes. You can put it in square brackets, because this is how we oftentimes write down comments in square brackets. Just a commentary, an explanation, additional remarks, substitution, or something like that. Anyway, so we cannot find this. This means that we cannot find the limit directly. What we can do is again try to simplify so that the zeros cancel out. So now it's not x. We take out what we see. Okay, x minus 1, nothing can be done, cannot be factorized. X plus 2, x squared plus 2 minus 3. Okay, x plus 3 times x minus 1. And now we see that the bad factor for this is again x minus 1. So we cancel out that. And we have remaining limit when x tends to 1 of 1 over x plus 3. That is 1 divided by 4. That's easily found. So again, you notice that basically, yes, if the 0 over 0 happens when x tends to some value a, then if you can factorize, then if you do it correctly, then the bad factor should be x minus a in both cases. It should be the bad factor. If we have polynomials, if we have a nice rational function like this, polynomial divided by polynomial. In other types of functions, it will be maybe different. So we take, we take the factor creating 0 out by canceling it, by dividing the denominator and numerator, and then as soon as we have done it, the limit can be found immediately. Another infinity. In this situation, we see, first of all, we notice that the power of infinity, the power of x, is different. So now we should divide out the highest power, and if you don't have the same highest power in denominator or numerator, then it's best probably to take the highest power of the numerator. However, you can simply look at the whole fraction and just divide out the highest power ever you see there. In this case, it is x cubed. So x tends to infinity. Infinity is what causes the problem. Let's try to get rid of infinity, which means divide by the highest power. All right. We see 3x squared divided by x cubed plus 16 over x cubed divided by x cubed minus 16 divided by x cubed. With a little bit of practice, it's algebra. If you are good enough at algebra, and this is the last example today, if you are good at algebra, you will be able to write this immediately without this middle part. You simply write down, okay, we will divide out x cubed and just do it and write, well, this is minus 16 over x cubed. When x tends to infinity, I repeat, this tends to 0, this tends to 0, and this also tends to 0. So what we have is 0 divided by 1. And that limit is 0. So we see that the infinity over infinity, this indeterminate form, we saw previously in the second example, we saw that that limit could be just the number, 3 over 2. And that limit, so it could be a number. Here we see it could be 0. 0 simply means that, see, the bottom infinity is stronger than the top infinity. In other words, this infinity is infinitely many times greater than this infinity. Sounds a little bit crazy, but it simply means that the denominator is infinitely many times greater infinity than the numerator. So if you can get your mind around that, you will understand that probably always when the polynomial in the denominator has a higher degree, then infinity over infinity will result as 0, because you will have a number here where the highest power was, but zeros with the lowest powers. And if the stronger infinity, the higher power, is in the numerator, then you would get a number there, but zeros in the denominator. Number divided by infinitely small will be infinitely large. So basically, if you have a, let's say, good understanding of comparisons of these things, you will probably able to just guess the answer, but you still should write down the solution just to make sure that everything goes correctly. However, some clever people can sometimes guess, or oftentimes guess, the value of the limit by just looking at that limit. It doesn't mean you can just plop down the answer. You still have to do the writing, but at least you know what you should be getting there in many cases. And now it's time for us to finish. So some people will meet for elementary mathematics in half an hour. I will be probably able to post the midterm examination groups tonight or tomorrow early morning. Not everybody is allowed to write the midterm examination, evidently, but I will set up those groups and post them tomorrow, the latest, because Friday, of course, it's too late then. The highest marks in unit test 3. You know what? With all this epidemic of cheating and all this huge crowd of people writing yesterday, I simply have no time to grade at the moment. So at this moment, I'm not grading until next week. Okay. Everybody is talking at the same time. Okay. So that's it. I will post the groups as soon as I can sort them out, but that will not be before very late tonight or early tomorrow morning, as I said.